Hi, this is Group 7. Today we are going to talk about Project 2, solar ethylene production from CO2 and seawater. Ethylene is an essential building block and also a common raw material for producing plastic. The demand for it is 152 million tons in 2016, and this number will increase by 21% in 5 years. The problem here is that the traditional way to producing it from cracking fossil fuel also produces a huge amount of the carbon dioxide emission. So our solution is try to use only the seawater, the carbon dioxide from the air, also the solar energy to create the green ethylene through the electrolyzer.
Our design basis produces 500,000 metric tons of ethylene annually. We'll leverage existing off-the-shelf technology where industry leaders exist. So for our direct air capture, which will supply carbon dioxide, desalination for fresh water, and PV panels for electricity, and then focus in-house on the newest technology where large efficiency gains are possible and device proof of concepts are still required. On the next slide, you'll see our electrolysis flow cell mock-up. We'll use a flow cell configuration that confers commercial benefits over H-type or microfluidic devices. We'll use an alkaline potassium hydroxide environment with the half reactions as shown. Our modular flow cells are scalable to larger stacks, even though there are limited economies of scale. And we'll use a cutting edge graphite carbon, nanoparticle, copper, and PTFE diffusion membrane, which will confer high selectivity, Faradaic efficiencies upward of 70%, high current density, and low overpotential. Our proposed preliminary plant location is coastal rather than sea-based. However, that's an opportunity for future development. We chose a spot that was close to seawater, had a history of high desalination capacity, has high incident solar radiation year-round, and potential clean energy tax and policy incentives.
For the technical calculation, so we try to build in the mass and energy balance for this project. First, we set our goal to 500,000 tons of ethylene per year. Then we use this number to find out how much seawater and the carbon dioxide required to achieve this goal. Using the overall reaction, then we know how we can distribute our energy generated by the PV panel to 3 portions: CO2 capture, electrolyzer, seawater desalination. And on the right side, there's a table showing us the detail of how this energy and the mass transfer goes. And the result, it seems like the majority of the energy goes to the CO2 capture. And if we want to reach the 500,000 tons ethylene goal, it requires us at least 9 million square meter PV panel.
Techno-economic analysis was conducted with a bottom-up approach, and some useful assumptions are applied in the TEA analysis as shown on the left side. In our project, the capital cost mainly consists of 4 different parts: PV panel, desalination unit, CO2 capture unit, and electrolysis unit. The price of each of them is found online, and some of them are scaled up to our requirement proportionally, namely the solar panels and the electrolysis unit. The costs are shown in the middle. Using the discounted cash flow analysis, the TLCC total life cycle cost of the system is found to be $1.78 billion. The levelized cost of energy, LCOE, is calculated to be 3.71 times 10 to the minus $8 per joule of energy. Next slide. The payback period of the system is also calculated as shown in the plot here. In about 3.4 years, the revenue would cover the insane upfront cost. And by the end of 10 years, we would be making much profit. However, note that we assume no degradation of our equipments, but 10 years is a long period of time, and desalination unit and electrolysis unit does not guarantee to make through the 10 years without degradation. Yet, considering that the cost of those two equipments are substantially small comparing to the CO2 capture unit, we believe it's reasonable to ignore their degradation costs.
So in conclude, even though this project has so many benefits, like it have the abundant raw material, only just the water and the CO2, and also from solar energy, and it's also environment friendly. It doesn't really produce any CO2. It's even use the CO2 as the raw material, but there's still many costs exist. And we believe in 5 and 10 years, the opportunities to increase the competitive can be achieved. Thanks.